On lesson 2, we're going to be talking about equivalent ratios. The vocabulary from yesterday talks about equivalent ratios is when you have two or more ratios that have the same ratio value. You can find an equivalent ratio to an existing ratio by multiplying or dividing the front and back terms of the existing ratio by the same number. For example, 10 to 5 and 20 to 10 are equivalent ratios because the ratio value is both 2. So equivalent ratios, so they have 10 to 5, I would write it like this, 10 to 5, and they have 20 to 10. Now when they look like fractions, they're ratios, but they look like fractions, what they're saying is the ratio value. When you divide this, 10 divided by 5, you get 2, 20 divided by 10, you get 2. So if they have the same value, they're equivalent ratios. There's a lot more ways to check for equivalent ratios than that though. We can also look, see how you're getting 2 times bigger on the bottom, and you're getting 2 times bigger on the top. So therefore, they're going to be equivalent ratios. We have many ways. We can multiply across, diagonally. They're both 100 when you multiply. So lots of ways to check to see if ratios are equivalent. And then just a reminder what the value of the ratio is, or the ratio value. It's a value that's found by dividing the front term by the back term. For example, if there are 3 dogs out of 11 pets, the ratio is 3 to 11, and the value of the ratio is 3/11, which if you change it to a decimal is 0.27 repeating. But I would just keep it as 3/11. So then let's review the ratios from yesterday's lesson. It says in the ratio 10 to 5, what's the compared quantity or front term? So when they say front term, that should be a lot easier than compared quantity. Just remember front term would be obviously the number in front, so that's obviously going to be the 10. 10 is what you're comparing. That's why we call it the compared quantity. What is the base quantity or the back term? Well, obviously the back term would be the second one, but remember that's also called base quantity. So our base quantity is a 5. What is the value of the ratio? So if I write it like looking like a fraction, that would be 10. The value is just by dividing them. 10 divided by 5, the answer is 2. So the ratio value is 2. And using students in the band at our school as your context, give an example of a ratio of 10 to 5. So we could just say for every 10 students in band, for every 10 students in band, there are 5 students in choir. My pen isn't working very well. So you can just write that example. Of course, we could have had that be anything. It could be for every 10 students in band, there are 5 students in study hall. Or we could have said for every 10 students in band that play clarinet, there are 5 students that play trumpet. So you can use any example or context that you would want in that situation. Okay, the compared quantity on that, we already wrote that, sorry, that was 10. The base quantity, that was 5. The value of the ratio was 2. And we just wrote the example right there. Number 2, what does it mean when the order of the terms in a ratio is reversed? And how does it impact the value of the ratio? Well, if we would reverse that, instead of having 10 to 5 and have 5 to 10, you should see really quickly that the value of the ratio is very different. Because if you take 5 and divide by 10, your decimal is 0.5. If you just took this as a fraction and reduced it, you could say 1 to 2. Okay? So it definitely impacts your value if you have the numbers in a different position. You're also saying if you wanted to use that same students, if you had 5 students in band, there are 10 choir students. Well, now it looks like there are less students in band than choir. Okay, on the next page it says, what is the ratio of the base to the height of the small rectangle? So let's just do that part first. So if we look at the small rectangle here, and they want us to compare the base to the height. So the fact that I see base first, I'm going to put that number first. So the base of this rectangle is a 4. Compare that to the height of the rectangle, and compare that, that would be 5. So I could write it like that. I could also write it like my fraction, so 4 to 5. Either one is acceptable. And then the question says, what's the compared or front term, and what's the base quantity or back term? So this one, the first one, obviously is the front term, or it's what we're comparing. So this is the compared quantity. And then 5 is the back term, or in other words, the base quantity. I'm going to really try to use the word compared quantity and base quantity as much as possible because those are the harder ones to remember. It's pretty easy to remember front and back, but we have to remember that they're also called compared and base. And then it says, what's the ratio of the base to the height in the big rectangle? So we look at the big rectangle. Well, the base is 12, so we would start out with the 12, compare that to the height, and that is 15. And when we want to label that, this first one would be the front term, or compared, and 15 would be the back term, or the base. One other question that you'd be asked, it's not on this page, is are these rectangles similar? Meaning, is one blown up to the same amount, increased the same amount if you blew it up on both sides? So like, for example, if the length got longer, did the height get just as long as many times long? So how you can figure that out is you can look at their ratio values. If you have 12/15ths and you reduce it, you would divide by 3. 3 goes into 12 4 times, 3 goes into 15 5 times. That reduces down to 4/5. So the fact that this one's 4/5 and this one's 4 to 5, but they're both 4 to 5, means they are similar to each other. This one is just a bigger model than that one. It's like if you put it on a copy machine and blew it up, you could get that bigger rectangle. Okay, on example 2, it says write the ratio of the base to the height for both the movie ticket and the theater screen. So I'm going to start with the movie ticket. The movie ticket's base is 4, so that would be the first number. I'm going to compare that to the height. There's my little keyword there. That's where your fraction line is going to go. The height of the movie ticket is a 2. So that's your movie ticket right there. I'm going to put an M for movie. And then the theater screen. This theater screen base is 8, and I'm going to compare that to, so that's where my fraction line comes in, to a 4. And this is the theater screen. So it's 4 to 2 and 8 to 4. The next question says, well, are they equivalent? Are the two ratios equivalent? And how would we know? Well, there's a lot of ways to figure out their equivalent. One is we could do their value. That's pretty easy to do with these numbers. So remember, the value is just the top divided by the bottom. So it's 4 divided by 2. That ratio value is 2. And then do the same thing for this one. 8 divided by 4 is 2. Since they have the same ratio value, they are equivalent. So the answer would be yes, they are equivalent. We definitely could have checked it another way to see if they're equal to each other. We could see, oh, you're getting 2 times bigger on the bottom. You're getting 2 times bigger on top, so that works. If you looked at your picture, you can see this is a 4, this is an 8. That gets twice as big. And the height is also getting twice as big. So as long as they're making the same amount increase multiplicatively, they would be equivalent. All right, in example 3, it says Mr. Smith and Mr. Plott are neighbors. Mr. Smith's garden is enclosed by 8-foot width, 8-foot by 12-foot length fence. And Mr. Plott's garden is enclosed by a 15-foot width by a 25-foot length fence. They drew pictures of it. Write the ratio of the width to the length of the two fences and calculate the value of the two ratios. So we'll start with the Mr. Smith's fence. The width, you can see, is 8, so I'm going to write an 8. And it says compare the width to the length, so there's my keyword, there's where my fraction line is going to go. And then the length would be second, and the length would be a 12. And then we can do the same thing for Mr. Plott's fence. The width is 15. Compare that to the length of being 25. All right, if we want to calculate the value of the ratios, calculating value is just dividing. 8 divided by 12. I don't have a calculator here, so I'm not going to divide that and make that a decimal. I'm just going to reduce the fractions as much as I can. I can divide by 4. 4 goes into 8 twice, and 4 goes into 12 3 times. So that ratio value is 2/3. You could also say, if you actually divided that out, it would be 0.6 repeating. Here we're going to divide by 5, so 5 goes into 15 3 times, and 5 goes into 25 5 times. So I can just leave that's ratio value is 3/5. Otherwise it would be 0.6 if you actually used a calculator to do it, change it to a decimal. Then it says determine if the values of the ratios are equivalent and explain. Well, we can tell just by the ratio value, they have two different values. This is 2 to 3, this is 3 to 5. They are not the same. So they are not the same value because they don't reduce down to the same number. Example 4 says a flag on a postage stamp measures 10 millimeters height by 20 millimeters base, and the flag outside school measures 4 feet height by 8 feet base. What are the values of the two ratios of the base to the height, and are they equivalent? So if we look at the first one, the postage stamp, the base first, and so they're saying the base first, so we have to start with the 20 compared to the height. That's your fraction line. Height is second. So it's 20 to 10. That's the value of that's the ratio of that, the base to the height. If I wanted to find out the value, I would just divide. So 20 divided by 10 is a 2. And then the flag outside, the base, so start with that number first, 8. And then compare that to the height, and that's a 4. And if you divide to find that ratio value, that is also 2. And so are they equivalent? Yes. A few people are very concerned because we're using different units. So on the postage stamp we use millimeters, and on the flag we use feet. As long as the units are the same within the ratio, it's still going to work. You're basically saying the top number or the base is twice as big as the height. So it really doesn't matter what unit you measure in. It would not work if one unit was measured in feet and one unit was measured in inches. Then we couldn't compare. But as long as within the same ratio we have the same unit, it works just fine. In example 5, it says Max is organizing his coin collection. For every 7 coins from Australia, he has 3 coins from Japan. And you can see right in the chart, they put that in there. So 7 Australian coins, he has 13 Japanese coins. The question is, what's the ratio of Australian coins to Japanese coins in Marx's coin collection? So they're asking for Australian first, so that's the top number, or the compared value. They're saying compare the Australian amount to the Japanese amount. This would be the base amount. So we took care of that's basically the ratio. We can't reduce it, so that's in perfect form. And then it says calculate several other ratios that are equivalent to the first ratio. So if this is 7, if this is 7 for the Australian, we could go, well, let's have them do another 7, so that would make it 14. And then we could go, well, another 7 would make it 21, and another 7 would make it 28. 7 more would make it 35. 7 more would make it 42. And then the Japanese coins, if it was 13, and then we doubled it, that would be 26. And we have 13 more, that would make it 39. I'm just basically adding 13, just like I added 7 on the top line. I'm adding 13 on the bottom line. 39 plus 13 is 52, and then 52 plus 13 is 65, and then 13 more than 65 is 78. So those are all other ratios that are still equal to the first ratio, because if we reduce that down, we still would get 7 out of 13 on all of those ratios. It says, what other ratios could describe this situation? Remember part to whole, and whole to part ratios. When you write the ratio, be sure to label the front and back terms. So we could do a lot with this. We could look at, let's talk about Australian to total amount of coins. So that would be 7 Australian, that would be your compared. I asked you to compare the Australian, that's your compared. So I'm going to put compared there. And, or in other words, front ratio. Compared or front is the same we're talking about the same number, compare that to the total amount of coins he has. Well, to find the total amount of coins he has, we would just have to add those numbers up. 13 plus 7 is 20. And that would be your back ratio, or in other words, your base quantity. That's just one example that we could have used. We could do a lot more. We could take the whole and compare to the part. Like we'd say, could take the total amount of coins compared to Japanese. That would also work. So it's whatever you want to set up as your context. It can really be any of those. Okay, now in example 6, it just basically says simplify the ratio 40 to 10. Of course, I'm always going to want to write it like this, so 40 to 10, and that's really easy now to simplify. You could divide both the top and bottom by 10. So 10 goes into 40 4 times, and 10 goes into 10 1 time. So that would be the simplified ratio. And then this one is 45 to 18. So there's a couple different numbers that we could use. We could divide both the top and bottom by 9. 9 goes into 45 5 times, and 9 Okay, question 8 says simplify the ratio 0.9 to 1.5. So the 0.9 is going to go on top, the 1.5 is going to go on the bottom, and we can't have a decimal in our ratios. We've known that for a long time. So one thing you can do to simplify that is you can just move the decimal to the end. I'm going to move that decimal back 1. If I do that in the top number, I'm going to do that also in the bottom number. Basically, I just made that number 10 times as big. So the top number is 10 times as big, and the bottom number is 10 times as big. So basically, I have 9/15 now. And I can divide both the top and bottom by 3. So 3 goes into 9 3 times, and 3 goes into 15 5 times. So that's a reduced ratio. And then we have example 9, 1.2 compared to 7.2. Again, we have that same issue, so we're going to move that decimal. I'm going to make that 10 times as big by sliding it over 1. Make that 10 times as big by sliding it over 1. So now we have 12 over 72. I can divide the top and bottom by 2. I can divide top and bottom by a lot of numbers, but the easiest one would be divide by 12. 12 goes into 12 once, and 12 goes into 72 6 times. That is what I just divided by was the greatest common factor. It was the biggest number that goes into both of them. So it's 1 to 6. And then finally, in example 10, simplifying this ratio, this is going to be the hardest one you have to do. If I write it, it even looks weird. 1/2 to 2/3. Just kind of like we did here, we wanted to get them to be whole numbers so we could reduce. We're going to try to make those whole numbers also. So if I multiply this top number by the same as the bottom to make that whole, that will work. If I multiply this number by 6, this, if you remember when you multiply fractions, this will cancel. So 2 goes into 2 once and into 6 3 times. So the top number I'm left with is 3 over 1, which equals 3. And the bottom, let's make it, if we made the top 6 times bigger, we have to make the bottom 6 times bigger. So I'm going to multiply. There's my shortcut here. 3 goes into 3 once, into 6 twice. 2 times 2 is 4 over 1, which equals 4. So now I have whole numbers, 3 over 4. That can't be reduced. That is a very unusual question, especially for a 7th grader. So don't worry very much about example 10. You probably will not be tested on that, but it's good to see what's going to happen in your future. In question 11, example 11, it says the table below gives the dimensions of several rectangles. Which of the figures are equivalent? So if we look at rectangle number 1 and we want to compare the base to the height, I would write 49 to 56. And then I would look at trying to reduce it, trying to make that ratio in smallest numbers as I could. I could divide the top and bottom by 7. So 7 goes into 49 7 times and into 56 8 times. I'm going to do the same thing for number 2, the base compared to the height. I have a 12 compared to 30. And what I could divide by there, the biggest number would be a 6. So 6 goes into 12 twice, and 6 goes into 35 times. And then this one, the base to height ratio would be 15 compared to 45. I could divide the top and bottom by 15. So 15 goes into 15 once and into 45 3 times. And last, I have 13 compared to 39. And I could divide both top and bottom by 13 there. 13 goes into 13 once, and 13 goes into 39 3 times. So this part says what figures are equivalent. Well, you can see these two have to be, because they have the same ratio value when they are reduced. And number 12, last example, an equipment box at the school gym contains 12 basketballs and 18 volleyballs. Find the ratio of basketballs to volleyballs in simplest or lowest form. So basketballs compared to volleyballs. So I see that basketballs are first, so I know the number 12 has to be right there. Compare that to volleyballs, that's going to be second. And then I do see the directions, it has to be in simplest form, which means I have to reduce that. Now a lot of you just say, oh, they're even, divide by 2. We certainly can do that. We can divide by 2, and keep doing that till we get to its lowest term. Or I can divide top and bottom by 6. So 6 goes into 12 twice, 6 goes into 18 3 times, and that is going to be your reduced ratio of basketballs to volleyballs.